register, this SCAS register, to see what caused the trap. So there are some things like instruction page fault, load page fault, another store page fault, environment call. This is the system call, environment call from S mode. This is the environment call from supervisor mode. And you have this other things like there is supervisor software interrupt, supervisor timer interrupts, external interrupts. So these are the external interrupts are the hardware interrupts, like from your keyboard and mouse, and these are the timer interrupts. So the timer interrupt will make the scheduler to come into context again and schedule the next thing. So after each time interrupt, this will happen, right? So there are these kind of important registers. So one is the STVEC. So this STVEC, this where, so this will contain some address, and that address will contain the function which will handle that trap. So there are two things. So there is a user vec function and a kernel vec function. If you see the x86 course code, so there is this. If you see the uh, trampoline.s, in this trampoline there are two functions. One is user vec and another is okay, yeah, user vec. Kernel vec is okay. Kernel vec, it's not here. Okay, so this is user vec, right? So this user vec function, what it does is whenever an event comes, like whenever a trap occurs, so there is a structure called trap frame. So the trap frame contains all the registers that are in the CPU. So we'll take all the register and store it in the trap frame. And the trap frame also contains some things called as this things: kernel hot ID, kernel stack pointer, kernel trap, and kernel satp. So these are, so for every process in user mode, there will be a kernel context also. So like a kernel mode stack pointer. So for every process, there will be a user stack and a kernel stack. That's why you have a kernel stack pointer, right? These kind of things are there.
So what is the use of kernel stack from the user?
Yeah. Let me tell you. So assume a user mode process is running. So it will use the user stack to compute its things, right? So whenever a system call or things like that happen, like some functionalities that need to be run in a kernel mode, then the user process should transfer to the kernel stack. It should use the things like when you make a system call, the system call needs to run, right? The system, for the system call to run, it uses the kernel stack, not the process stack, right? Not the user mode stack. So the kernel mode operations occurring in the process due to a system call or interrupts like that will use the kernel stack. Okay, interrupt handling, all the interrupt handling and system call handling will occur in kernel mode, not in the supervisor mode, right? So
Yes, yes.
to that operations, we need a kernel stack.
So it will be common to all process, right? All process will have same value for kernel stack pointer.
No. Every process has its own kernel stack. Every process, like, so assume process A is trying to read from a file, then it should make a system call, right? So then process A, the this kernel system call will be running, right? So it runs. So to run that system call, it needs a stack, right? So that uses that's a kernel stack for process A, user process A, and user process B will have its own kernel stack. So there is
Okay, we got
when
it.
the okay. So there is the main kernel thread will be running, right? So the main kernel thread from is starting from the start.c. So not start.c, the main.c. You can see this is the first thread that happening. Scheduler will be taking up, right? So this is the main thread that is running, and after the first process starts, it forks from the the user init will happen, right? The first user process will begin. This after user init, the scheduler starts, and the scheduler will schedule to the user process, first user process, right? It will go to the first user process, and all other user process are forked from the first user process. And each process will have a kernel page table also. The user page table and the kernel page, not a kernel page table will be same. A user stack and a kernel stack. The page table for kernel is same. Okay, we have only one common kernel page table and different user page tables, but the kernel stack is different for every process. Okay.
Yes, sir.
Yeah. So we have this trap mechanism, right? So whenever a trap occurs, we need to know where we want to go. So that instruction, what to run after when a trap occurs, is address of the next instructor to run when a trap occurs is stored in the STVEC register. Okay. So usually when the process is in user mode, it will contain the address of this user trap, user-vec function defined in this thing. And this stores all the registers and these things and change to kernel page table. You can see. So now we are changing from the user page table to the kernel page table. So the kernel stack page SATP will be present in the trap frame. The trap frame will hold the information regarding to the kernel stack, the kernel SATP and things, the kernel art ID. So the kernel mode parameters. The trap frame will have the kernel mode parameters as well as the register used to do that user mode operations. So we'll load all these and we switch to kernel mode. We change the page table. So page table SATP register, right? So we change the SATP register to the kernel page table. So now we are using kernel page table. So then we are jumping to this user trap function here from here. So this user trap function is defined in the trap.c. Okay, this is the user trap function. So this function checks for the reason for the trap, right? So we are in user mode. Then the STVEC contain the user trap function, user vec function, and the user vec function stores whatever is in the register to a thing called trap frame and comes to handle that trap in the kernel mode. So now we are in kernel mode, right? We change the page table. So we should make this thing kernel. This STVEC is that register to where to go when the trap occurs. So now since we are in the kernel mode, we should make that STVEC to point to kernel trap. So there is another trap handler when in kernel mode, which is called kernel trap, kernel vec. So we write the value of STVEC as kernel vec, which means now the value in the STVEC will be written as kernel vec, and the kernel vec, I think it's present here in this file. Okay, this is in kernelvec.sr. Okay. There is it. Here the kernel vec is present. So this is what to do when a kernel trap occurs during the kernel mode. It saves the register. So it's also saves these registers. You can see. And this is how to handle the other interrupt, right? So this is how to handle a timer interrupt. These things are there. Okay. So first saving part is done by user vec and handling part is done by user trap. So while handling, we'll change that to kernel vec, the in STVEC to kernel vec, and then we'll store the exception program counter to that the program counter of the user process safely there and check for the SCOS. SCOS register is this thing, which will have the code for the cause of the trap, right? So there you have these things. So we'll check these things. So if it is 8 means it's a system call. You can see that here. It's an environment call from user mode, system call. So then we call the system call function, which will in turn identify the what is the system call that occurred using the A7 register, I think. Yeah, you can see that here also. Okay. So, click searching. It's defined in this syscall.c. You can see that, yeah, all the system calls are there. And this will check the A0 register. Yeah. No, A7 register, which will have the system call number and calls the system call, which the relevant system call, and returns that value to the A0 register. So that's what that is. So if it is
A7
system
has
call,
8. A7
sorry,
has 8.
A7.
Has 8. The number 8.
No. A7 don't have the number 8. The RCOS register has this number 8.
Okay.
A7 is this is the ISCOS register. This identifies the reason for the trap. The A7 register has the system call number. Every system call has a unique number. If you see here, you can see all system calls are placed in an array of function pointers. This is, and this is the first 0th index. It's at first index, second index, and each system call has its own index, right? So that number represents the index. Okay, so we get the system call present at that index and call it. What is that num? It's the value present at A7. Okay.
Okay, got it.
So now, if it's a system call, we'll handle this. Else, so there is another function to handle device interrupts. So this will this will call the function device interrupt. It's defined in, I think, this kernel vec is defined in start.ci. So let me check. No, it's in. Sorry, which function are we checking? Div enter, right? So I think I should log in so that we can easily browse through these files. So there is this div enter function. Yeah, here. So it will see the SCAS register in 10 again, and if it is 9, you can see that this code is actually representing what is the value of the register, and that is actually corresponding to this thing, 1 and 9, supervisor external interrupt. So it will see that it's an external interrupt. You can see the code like this. If it's an external interrupt, and so this, what this 8 means, which means the last bit is, the most significant bit is 1 and all others are 0, which means it's essentially checking for this number, the last bit, this bit. If this is an interrupt and the code is 9, It's a supervisor external interrupt, right? So that's what this says. How to handle this from a UART, the IO disk interrupt, how to handle that is all there. And there is this one, which is machine mode timer interrupt. You can see that here. Where is it? 8, 8, and last thing is 1, which means 100. This is 9. Only last one means it's 1, right? This thing. Okay. Yeah, actually the machine mode timer interrupt will cause a supervisor software interrupt for the timer to run. Okay, so this is happening from the timer vec function, which is in the kernel vec s. If you see, when a timer interrupt occurs, this will check for the timer interrupt, schedule the next timer interrupt. You will see it's in this week 6 only, and it will, yeah, this SIP register is this. Okay, let's see. Yeah, yeah, it arranged this as a supervisor software interrupt, right? So whenever a timer interrupt occurs, this timer vector function is called, and there's some things called as this time compare registers are updated, and it forwards it as a supervisor software interrupt. So that's why we are checking that number, and we'll get this supervisor software interrupt. And okay, we will trap.c user trap, and these kind of things will happen. So we check for whether it's a timer interrupt or things. So if the dev enter function, you can see that things are happening. And then other thing is this: when timer interrupt happens, it actually returns to. Okay. So by seeing the value of the return for dev enter function, we can see that now it's a timer interrupt. So we have to yield the CPU, which means give up the CPU. So if you see otherwise, this won't happen, right? Just handle that trap, handle whatever is the problem here, and then return the trap. That is for what's user trap rate. So there is this user vec, which will save the trap frame and change to kernel page table and kernel stack pointer, and then we come here and execute the user trap, right? User trap function, and handle the trap. If the trap is timer interrupt, we don't return directly from here. We go to yield, which will take us to the new context. So after coming back, we'll return to the trap. Okay, so if this is not the case, we'll just return to the user mode using user trap ret. That's why user trap ret, return from the user trap. So for that, what we do, we again change back the user vec. So here we changed the user vec to kernel vec. Now we change back that to user vec, and then store the kernel trap point, trap, satp, and everything back to the kernel vec, the trap frame. And this is set the status registers. We will see what a status register is, and the program count. This program counter. We are restoring the program counter from the trap frame and putting it in the SCPC, and going back to the user page table. So p.page table, p is the current process. We are going to the user page table. Then we are calling the user ret function from the trampoline.s. So here there is a user vec and a user ret. So user ret is the opposite of user vec. So this will store all those registers. This will load back all those registers. Okay. So this trap is fine, right? How a user mode goes into kernel mode and execute a trap, handle a trap, and then come back to user mode. So if the trap occurs to be a timer interrupt, the process will yield itself. So we saw that yield function there, right? So usually these things like, okay, where are we? Here. So these are that interrupts, right? So all these interrupts are handled in that way. The STVec will contain the user vec address, and we move to the user vec, save all the registers to trap frame, then call the user trap, handle the trap, then check whether it's a timer interrupt. If timer interrupts, yield that, else come back to the user root using user ret, user trap ret, and in the user trap ret, after changing all the kernel things to user things, we'll restore the registers also. Okay. So then the other thing is context switch. When timer interrupt occurs, we have to worry about context switching. So that's when this happens, yield. So what does yield do? Okay. Here in the proc.c, it just acquires a lock. So just to make it synchronizable, and it changes the state to runnable, which means it changes it from running to the runnable state, and then call the shed function. The set function will do some checks. If you see, it will do some checks like this, the logs, the state is that, and after that checks, it will call the switch function to switch the context. So p dot context is the process context. So context is actually a structure. If you see, there is this thing. Proc.h, you can see it's a structure, and the trap frame is also a structure. If you see, right, this trap frame has all the registers and some additional things like kernel RTID, exception program counter, kernel stack pointer, kernel satp, kernel trap function, these things. Okay, this context will have a subset of that, only the return address, stack pointer. So this context will be something in a kernel thing, right? So this context is a kernel thing, kernel's context. So this trap frame is like the user mode context. So it has to also know the information about the kernels of the user process, right? And here, since we are in the kernel, we'll change from the one process to different process of the kernel using this context. So we need not store these temporary registers, these T things and these A things. We just store a subset, the saved registers and the stack pointer and the return address. So that's how we change. So we change the return address and all these things so that we go back to other context. So here in the set function, we'll call the switch function. We'll change from the current process context to the CPU's context, which means this is the scheduler's context. When this is called, you can see actually the switch changes these things. So the switch function is defined here. It's from the switch.s. It basically copies the thing, copies those registers, right?
Sir, I have a doubt.
Yeah.
Sir, process context makes sense, but what is a scheduler's context?
So okay, let me see. When in the first main.c is there, right? When the main.c starts, in the main from the main.c, when the here, user init will happen, and finally this will be running, right? So what is this? Actually, from the scheduler, when the first user, what scheduler does is also the same thing. It also uses the switch function. You can see that here. The scheduler, while running, finds a process, a runnable process, and make it running, and switch from the scheduler's context to the process context, right? So whenever a process want to switch, it comes back to the scheduler here. When a process is done running, we'll come back here, right? So we go from here. When we come to this line, we'll go to the first user process, because at first that only will be runnable. The user init function will set the state of the first user process to runnable, and we will find that that is the only runnable process. And when we find, we switch from the scheduler's context to the first user process context in the kernel mode. And from the kernel mode, we also use that I think it's forkret. There's a function there, and use that forkret. We go to the user mode. Okay, so from that switch, we come back here. So when that switch occurs, we will be here in the scheduler. Okay.
Sir, context just means that there are saved registers, right? S from S0 to S11.
Yeah, the return address will be there. So what is the return address? Where to go next?
Okay, okay. So that will be changed to this scheduler.
Yeah, this line. So it will come back here. Okay, this line. It will. So actually, let's see. So the my CPU will also have that context thing, right? When we switch from one thing, you can see the switch. Is that switch.s? Yeah, here. You can see the return address is also stored, right? So which means the return address will be, say, the current registers, not is all with the stack pointer and the return address. So return address is the next place to go. Okay, stack pointer is the stack, the pointer to the stack, right? And these are the saved registers. So since we are loading this return address of the scheduler when we come from the process to here, and we are returning, where will we return? We return to this return address. Okay. When we call switch from scheduler, the return address will be stored. And then when we come back, it will be loaded and we return. So we go to the return address, back to the scheduler. Okay.
Okay, sir.
So then we come here, and scheduler schedules the next process and changes the context of the scheduler to the next process context. And when it goes to the next process context, it will be going back to its kernel thread, right? So when we switch, we'll going back to its kernel context. So where it will be, so back to here, from switch to user displays, user trapret. Where is it? There to here, because the other process may have left from here, right? It may have yielded from here, and that will be the kernel context will be here. It may have, so whenever the other process may have yielded and our previous process was running, and when returning, it will come back here to the other process user trapret function. And similarly, we go back to the kernel we'll save that kernel registers to the trap frame and go back to the another process user space using user trap ret, and which essentially calls the user ret function of the that trap frame. Okay, in that process trap frame. So we change the page table, right? Okay.
So the value of the CPU context never changes. It remains to the scheduler, the return address.
So this there is this my CPU function, right? So what this my CPU function has? Here, yeah. It will take the CPU IDs, and there is a struct CPU is there, which is defined here, which will have the current process running, the CPU's context. So there will be a CPU's context, and here is where the scheduler is. Switch here to enter to the scheduler, right? So this scheduler's context will be stored in a structure called a CPU, and in that structure there will be a context, and there is where the scheduler context will be. Okay.
Okay.
So when we call my CPU, we'll get the CPU structure for the corresponding CPU. So there is this CPUs are there. If you see, there is a CPU and CPUs. So there is an array of CPU structures where the end CPU will be the number of CPU present in your machine. So there will be array of CPU structures will be there, and each will have its ID, right? 0, 1, 2. Using that heart ID, we'll go back to the CPU's context. So each CPU initially will have the scheduler context, and the scheduler changes its context to another user process, right? And then come back to the scheduler and go to other process, and then come back to scheduler, go to other process. Okay. So this going from kernel mode context switch. So in the kernel mode, you will go from one kernel mode to one kernel mode of the one process to the CPU, and CPU to the other process. This is called context switching. So trapping and trap return is like going from user mode to the kernel mode of the same process and going back to the user process. So in whole context switch, when in user mode, we'll trap to the kernel, and it will handle the timer init, timer interrupt by switching to the CPU, giving the CPU up, and the scheduler will schedule to the enter to the another next process context, and from there we return to the user mode using user trap ret, which will call the user ret function by restoring the user mode register values. So for user mode, there is a separate register values, and along with that, the kernel mode values will be also stored in the trap frame. For kernel mode context switch, going from different kernel mode processes, we use a structure called as context, and the CPU's context is the scheduler's context. Right? Each CPU's context is the scheduler's context, which is the first program that is loaded into the CPU. Okay. Now you get that? Any doubts?
So I joined late, so can you just again tell about the timer init function? How the timer interrupt happens in the code?
How timer interrupt happens? Okay. So when timer interrupt happens, this thing like when any interrupt happens, the value in the SCOS register will be updated corresponding to the type of the interrupt. So for timer interrupts, the machine mode timer interrupt, it will forward the machine mode timer interrupt as the supervisor board software interrupt. That is written in the timer vec function, which is defined in the kernel vec.s. So there is this timer vec function, which you will see this timer vec in this 6 weeks, the last timer interrupt function, like lectures, I think. So there is this m time and m time compare registers, which will tell when the next timer interrupt should occur, and the timer init function will set this up, and this timer interrupt will check this thing, and whenever this time compare is going after that, like after a certain interval, it will raise a supervisor software interrupt. This will raise a supervisor software interrupt.
So how does
So
this
when
function execute? Does it execute in parallel to other processes, or
no
it's a hardware feature?
interrupts will okay. So machine mode timer interrupt occurs, right? So there is a mcos register also. If you see, there is a mcos. Whenever an interrupt occurs, this mcos register is there, right? Its value will be updated. A machine mode timer interrupt. This value will be updated, and the machine knows there an interrupt occurred. Okay, so there is a register called, just like the STVEC, there is a MTVEC. Whenever a trap occurs, this thing, whenever an interrupt occurs, the program will check this register to go where to how to handle the interrupt. That is a trap. Okay, so here's this machine mode interrupt will say that a machine mode timer interrupt occurred, and that machine mode timer interrupt forwards it. Let's see. So where is that? Yeah. So the start.c has one function. Timer init function. So this deals with that m status, that mtvec. You can see this mtvec register is here. It will set up machine mode trap handler to the timer vec function, which means whenever a machine mode interrupt occur, you will use this function to handle that. So whenever a timer interrupt occur, it will check the value at the mtvec, and this is how you handle that interrupt. So whenever this interrupt occurred, we will go here. So this is just the setup, and we'll set up that here or here. Where is it? Where is this? Yeah, here. We set up that timer, enable the timer interrupts in the start function. Okay, and there is this timer interrupt enabled. All the registers are set, and this mtvec register will point to the handler, how to handle that timer interrupt. And what is the timer vec? Timer vec is present in the kernel vec.s. This specifies how to handle a timer interrupt. So whenever a timer interrupt occur, the control will come to this timer vec function. Okay. So all the traps are handled by the functions that are present in that vec register, mtvec trap vector, which means mtvec is machine mode trap vector, supervisor mode trap vector is stvec. So whenever a supervisor mode interrupt occur, it will check the stvec register to go to the program, go to the handler, how to handle the function that handles the interrupt. So the timer interrupt are handled by this timer vec function, right? So this will in turn forward the timer interrupt as a supervisor software interrupt using this SIP register, writing this value to the SIP register. It will do that. So a software interrupt occurs. So the STVEC register will, when the software interrupt occurs, the STVEC register should be handling that, right? And the STVEC register, when in user mode, will contain this user vec function. Where is that? User vec function is in the trap.c. Is this? Oh, no, it's trampoline.s. Here the user vec function is there. So this is the default trap handler for user mode traps. So the STVEC will contain this function. So whenever an interrupt occurs in user mode, it will use this function to handle, and there is a kernel vec function that's used to handle the kernel mode traps. Okay. So in the user vec function, you can see what we do is save the contents of the trap frame and change to the kernel page table and jump to the user trap function. And what is the user trap function? It's in the trap.c.
Yes, yes, yes. I'll get it.
Okay. So that is how this user trap is the trap handler. So we go to user vec, store the trap frame, come to the handler, check, handle everything. And then if it's a timer interrupt, we don't go back to the user mode using user rep, but we yield this CPU and go to this yield calls the switch function, the shed function, and the set function will check for some checks and call the switch function to switch to the context of the CPU. And that CPU context is the scheduler's context. Scheduler will then schedule the function and come back to the next process context. And then when it comes back to the another process context, it will come here because the another process would have yielded that before, right? So it will come here and run the user trap ret in the another process context. So it will then load the user process trap frame and the page tables using the user trap ret. Okay.
Can you show the code where this timer interrupt is triggered? That M time.
Okay. So this timer interrupt is triggered by the timer itself. Okay. We only store the address of the timer interrupt handler. And how do we set that timer interrupt handler? Which register should contain? The empty vec. Empty vec register will contain the address to go whenever a timer interrupt occurs. Okay, empty vec register will contain that. Where we set that empty vec register? In the timer init function, and which is called in start.c. Here we set that empty vec should be timer vec, which means whenever a timer interrupt occur, you should go to the timer vec function. So that's what we say. So the timer interrupt is raised by the timer. It's a hardware component, right? It makes a timer interrupt, and this empty vec register will have the machine mode trap vector, which means when that trap occurs, that interrupt occurs, we'll go here. So this is just specifying where to go when this occurs, whenever a trap occurs.
So it happens when M time is greater than M time CMP.
Oh, that you are asking about that thing. So
Yes.
that is actually raising that interrupt. So whenever a timer interrupt occurs, we go to timer vec, right? So in the timer vec, which is defined in the kernel vec.s, here you can see, yeah. So the timer interrupt actually occurs using by the timer. It occurs. So there are two registers. Here it is. M time and M time compare, right? Here,
Yes.
here they are. Yeah, there are these two registers, right? So these, okay. Okay, this code is actually, I think, this is where this is there. Okay, this comparing thing. Price. Okay, let me check. This value of this M time register will be updated by the CPU clock itself. And okay.
Reading that paragraph, it looks like the practice assignment question 1 is wrong.
Which one?
In week 6 practice assignment question 1, it says here that interrupt occurs whenever M time contains a value greater than or equal to M time CMP. But in practice assignment of week 6 question 1, the correct answer is when it is greater than, not doesn't consider equal to.
So where it is equal to? Here, which line are you reading here?
Top of the page. Yeah.
Here?
Yeah, that second paragraph. Yeah. Machine timer interrupt.
Greater than or equal to the M time compare. Oh, in that question, it's given only greater than.
Yes, but there is an option also for greater than or equal to.
Okay. Okay, we have this greater than or equal to also and greater than also. But this is not given. This is given us the correct answer. That's what you're saying.
Yes.
Okay, so okay, what is the part of code that checks this condition? Let me go through here. Let me check the OS part. Okay. This is just scheduling that next timer interrupt. Okay, then we'll check this question, how this occurs, the checking part, where does it happen, and we'll update it accordingly.
Okay.
Okay. So whenever that occurs, you come here to the timer reg, but I am not sure where that occurs, how that occurs. I think it's the timer will read the values of the M time and M time compare register and cause the interrupt. But I'm not sure which is that. Okay.
Is it possible to change the value of M time CMP?
Yeah, we have to change the value of M time CMP. M time is controlled by the clock. M time compare. So it's like M time is the current CPU clock time, and M time compare is the clock next time to cause the next interrupt. So now, if the time to cause the next interrupt is happened, we'll update the time to cause the next interrupt as the next one, right? We increase that time. That M time compare will have the time of next timer interrupt. So we should update that whenever we see a timer interrupt. Okay. This M time register will be updated by the clock. In every clock iteration, it will be updated.
Is there some place where the M time CMP is set in this code?
Yeah, here it's adding, right? So this, let me check. Yeah. A1 register. This is M time compare of the heart. So each
That is, you are taking, in this code, in this line, you are taking the value stored in A0 and storing it in A1.
yeah, so this is the m time compare, already existing m time compare value, and this is the interval, and we are adding that to here and saving it A3. So what it seems. I'm not sure about this code also, but it's saying that we are changing that m time compare by adding that interval. So it's loading A1 of A0. So what is in A0? This M scratch register, right? This is so this is the, yeah, 24 is the address of M time compare register. So they are taking that 24, the value of the M time compare register, and adding that interval M time 32. This place we have the desired time interval. So we are taking that. Then what is the 0? The 0 will have the register save area. So where should we? I'm not sure about what is this. Let's see about a scratch. This is machines mode. Scratch. What is the scratch register? Hold a pointer to the context. So I'm not sure about this. What is the scratch register? But it seems the M time compare values are coming from that register. Okay. So this is the address of M time compare register. Not sure how this scratch works, but what it is trying to do is this thing, updating the interval. I'm not sure about the exact code also. Okay.
So later, can you when you figure out, can you just make a post on Discourse if possible, like how this timer function works?
So how it works is given in comments, but I am not sure about the exact things, right? So it's just
suppose you want to give more time on a processor for one particular process, then do you change the M time CMP for that, or
so that will be like decided by the yeah. No, not M time compare. There is a interval, right? Interval is stored in the this scratch registers 32 address 32. So a scratch register, why it's not given which point is used for what, but it says that used to hold a pointer to the context, trap handler and things. I'm not sure why it's used to store this thing. But here it's storing that scratch register is storing this thing. So here in the interval, so let's see whether in start.c it's available or not. When we are setting up things, start.c. Yeah. Yeah, here they are setting up these things. Here is mclint mtime compare. We are setting that here. So there is mtime compare register for each heart ID, and there is this interval. Here is that interval. This many cycles. If you change that here, timer interrupt will occur for every this many cycles. So we are storing that interval value in this scratch register. Yeah, it's happening in all the setup of the how timer interrupt should occur is happening in this timer init function. They are setting using that scratch register. I am not sure why they are using that scratch register, because it doesn't have, I'm not sure about this. So they are using this to save the m time compare and the interval for that. Okay. So we are setting
Suppose
using
I
that
change
register
that
to store
interval,
this. Yeah.
suppose I change that interval to a much smaller number. If I make it
Then
100
you
or
will have
something.
a much frequent timer interrupts.
Okay. So it will be possible to see that if you are executing two concurrent processes or something.
So for every process, so it's the main timer interrupt, right? So timer interrupt happens frequently and context switches happen frequently. So the scheduler will schedule. So there is a time quanta we allocate for the scheduler, right? Usually, so that time quanta is this interval.
Okay.
So when you study scheduler algorithms, there will be a time slice. So at each time slice, the scheduler will decide on which process to execute, right? So that this time slice is that where at what time you should go back to the scheduler and check next. So you may switch back. So in scheduling algorithms, if you see after each time slice we check, but in some time slices maybe we'll come back and execute the same program itself also. So our xv6 code doesn't schedule like that, but there are some scheduling algorithms like shortest job first come first serve. This kind of things are there. So for that we may schedule the same program also. You can also add that features to the xv6 code if you want. You can change this value to make the context switch happen more frequent, go back to the scheduler more frequently.
Okay.
Right. So this m time, uh, there is this register is thing. Yeah, there is this m time register, and we are taking the address of value at the address of m time register and adding that interval to the this thing. So this is where we set up the things. So that's what we are checking in the timer vec also, the handler. So we are checking those registers, changing the values. And when that happens, it this register prints address of the okay. So this Clint is the interrupt controller. So I think we are placing that value here at the address. So this 24 is the address. Here A 24 of A1 is the address. And you can see we are storing the result in the address of the interrupt controller. So that interrupt controller will know when to cause the next timer interrupt. We are placing the m time compare value. So this is the address of the m time compare value in the local interrupt controller, right? So we are placing in that address, this address A1. A1. We're placing the value of the result A3 to the. So this is loading the value of that. Yeah. Oh, sorry. The network problem. So here, what we are doing, we are loading the address of the. Okay.
Screen.
Before it was visible, right?
Only 1 minute. Right now,
Yes.
30 seconds or something.
Okay. So till now you don't see my code.
No, it's visible.
It's visible.
No, it's
Only for 1 minute it was not visible. Okay. Yeah. So here we'll take the interrupt value from this scratch register and the address of the client mtime compare, and we load the value present at the address of mtime compare. So we load the value from the mtime compare and put in the A3, and we add that interval to the address of mtime compare, so that our interrupt controller will know when to cause the next interrupt. And after adding, we store that into the interrupt controller's address. AA1 is the interrupt controller's mtime compare address, right? So there we store it so that the interrupt controller will know when to cause the next thing. Okay. So the interrupt controller causes the interrupt. We communicate with the interrupt controller to schedule the next interrupt. Okay. It's much like sending a value to the monitor or something like that. Okay.
Okay.
And it automatically causes the next timer interrupt during that time. And we handle that using this timer vec. We update the mtime compare again, and then we change this mret. So we we raise the supervisor mode software interrupt and return from the this thing. So it will cause a supervisor software interrupt, and that supervisor software interrupt is handled by the kernel vec function or the user trap function. This user trap function will handle all those kind of interrupts here. So when a interrupt occurs during the kernel mode, it saves those registers and it goes to the return to what we were doing in the kernel. What is this? Call the kernel trap. Okay, so there is a kernel trap function also here in the oh, I'm not sure why I'm disconnecting often. So till when where I left?
2 1.
So here the kernel trap and the user trap will be similar, but only this system call handling part will not be there. You can compare those things. There, this is the device interrupt handling, and the timer interrupt handling part is there. The system call part is not there. Otherwise, it will be checking the statuses. So this status SSP will be supervisor's previous mode, right? Here it's not equal to 0, which means we are not from the user mode. And here it will check the same thing, but it's equal to 0, which means it's a supervisor. Okay, where's it? Okay. If it is equal to 0 means it's not a supervisor mode, right? It shouldn't be. If it is 1, it is supervisor mode. If it is 0, it's user mode. It's like that. They're checking that this just to check everything, whether this trap is cast correctly, and then this is device interrupt handling, and this is timer interrupt handling, the same things. And here we just change these things to restore these things. Okay. So most kernel trap and user trap will look similar, except the system call handling part. Okay.
In the beginning, you had shown one that cause register with starting with 8 in the most significant bit. No?
Yeah. So
And
cause
getting the-
register. Yes, cause register. This one. Yeah, most significant. That is in hexadecimal. If it is 8 pins, 10000, right?
Yeah. So in that,
That's-
I think in the code when you showed it, it was ending with L.
So L is just to specify it's a long. I think I'm not sure about the L. I'm thinking it's long float. Like how many bytes to use? 64
Oh.
bytes, things like that. 64 bits,
Okay.
maybe. Yeah. Because everything is 0, right? So it may use a small number so that they put an L to make sure that it's a long value. I'm not sure about that L also. I think it's that. Any other thing?
Yes, it's for long. The stack exchange it's for long.
Okay.
Sir, I have one basic doubt. Like
Okay.
there are some files like .s, the assembly files.
Yeah.
How are they called in the C program?
So actually the C program when compiled so everything will be compiled, right? Everything will be compiled into machine code only at last. This is just the source code, right?
Okay, so does that make file is
When
responsible
compiling, the
for?
compiler will figure out which function and where is that, and the compiler will translate everything to the machine code. So the names you see will be automatically linked by the linkers. Linker will search for this function, and that's the compilation process, right?
Okay, basically in C code we used to add hatch include for linking other files codes, right?
Yeah,
So for .s files we don't need to do anything.
they are also including things. So here,
Like
if
when
you
it's called
see,
somewhere else.
okay, so you're saying, uh, yeah, the .s is not here. Maybe I'm not sure about that, but I think compiler should be handling that assembly code also. So which there is this make file, right? This is how the compiling instructions are. Yeah, okay.
Hello.
Okay, I'll read that. Why it's cutting here? So I'm not sure about this. I think these instructions should handle those. Compiler should be able to handle. I'm not sure about how that exactly thinks, but it's doing something with these S files also. That's what I know. So I assume compiler is taking care of whichever functions is defined in whichever S files or the C files.
Okay, okay. So can you also just tell about that dot section and dot global? What significance does those things have
What?
in in assembly files above the functions? You define the section, global, align.
Okay, so I'm not sure about that also. Okay, maybe this is defining that as a global function or something. I'm not sure about this. I'm actually I not know assembly code. I'm just assuming this is what happening. Like, so since you are also not very much into this assembly code, and our course also not focuses much into this assembly code, I am not sure what is this, but this is like functions. That's what I assume. These labels are like functions and which will have addresses, and that addresses we can refer in other things. Like if we say it's same as the function address of a function in C, this behaves same as that. So I use some kind of analogy to link between assembly and C. That's it. I'm not sure about what this global section and things. So
Okay, sir.
yeah, I just use this comments to guess what that assembly code is doing mostly.
Yeah, me too. While reading through this code, I use these comments as what they're doing.
Is it possible to see what values the registers are holding while this is running?
So in that, I'm not what value the registers are holding. Actually, yeah, you can see using, you can create your own system call and you can get that. You can actually do that. So you have to create a system call, register it, and in that system call, you should use these functions like rstvec and things like that. So when you call it from the user mode, it will go back to that and see the value of that registers and put that back to you. But I don't think it will have the exact values when you called it from the user mode, because this stvec will change, right? When you are in kernel mode, it will be pointing to the kernel vec. So you can see that address. So that's that kind of things. You can see all the registers using in the machine mode. When you are in the machine mode, you can see all the register using a system call. So that will print that to the user mode. You can do. You have to modify the XV6 code to see that.
Could you show how to do it next live session or something?
So maybe I'll show how to create a system call first. Then I have implemented, I think, yeah, okay. So I have added that as the one of the exercises also. You can create a system call to if you want to create a new system call, you can easily do that. Maybe we can see it in the next live session.
Okay, okay.
So anything if you want from the machine mode, you can create a system call, so that you have to modify some files. Like there is this user use is PL. So this is the things that contain the system call things. Okay. This will, you have to add the new system call here. So and create the corresponding function in any one of the files. Yeah, you can create your new file also. So when you call that function, this will register that function to call that system call, and you have to also register that in here. You have to add that number, and that's it. So, and I think you have to add that to the here also. Here
So
also.
.pl file is a Perl file. What?
Yeah, that's actually creates mapping for the mapping to call the for each system call. We have to call the eCall instruction, right? So this is expanded during the this file will be generated. So uses.s file will be generated from this .perl file. So this program will create an assembly code. So this is an assembly code. You can see this, right? An assembly
Yeah.
responding to each system call. So you can see here, this is just loading that system call number to the A7 register, calling the eCall and returning. So the uses dot s assembly file will have these assembly instructions to call the system call.
So basically uses.s is created by this code.
Yeah, this Perl file.
Okay.
I think a line for that will be available in the make file also. So make file will contain a line to do this. Yeah, this thing. Perl will be called, and this file will be run, and the output will be stored in the uses.s.
Okay. Thank you.
Okay, then.
We can find it.
Okay, then. Thank you, everyone. We'll end this session.
Excuse me, sir.
Yeah.
Yeah, I'm sorry. I joined it a bit late. Don't know what else happened in the session, but I just wanted to clarify one thing. I saw your response to my question on the chat space regarding
Yeah.
the exit function. So
Yeah.
from what I've understood is that the exit function changes the context to the scheduler, and then it is left up to the scheduler to decide what to do next, and that is how that works. Am I correct? Is my interpretation correct?
Yeah, actually. So when you say, when you let me share my screen again and go walk through you that situation. It's kind of that. So what happens is when you call exit, in the proc
Yeah,
dot,
yeah.
I'll go here and sys proc dot c. So when you call exit, oh yeah, here what happens is,
Could you zoom in slightly to the code, please?
yeah. Okay.
Yeah, much better. Thanks.
So what happens is you do all these things. So like close every file. In exit, you close all the open files and change the CD, reparent any children to there, wake up the parent, which means we are just setting the state of the wake up. This wake up function is just setting the state of the parent from sleeping uh, sleeping to runnable. Sleeping to runnable, and here the exit status will be stored in this xstate field, and the state of this process will be stored as zombie, and here it jumps to the scheduler. You can see that, right? It doesn't jump back to the parent, it jumps to the scheduler, which in turn calls the switch function to go back to the scheduler's context, and from there this function never returns anything. This exit function never returns anything to the parent or anything like that. You just go to the scheduler, and the scheduler schedules the next process. But when the next process, when the parent will get its chance to run from the scheduler, it will run, and there the parent will be calling the wait system call, right? So it will be calling the wait system call. So wait system call is basically check whether any child has exited or not, using this zombie function, and release all the resources. And if we are still waiting, it's just sleep, right? mean don't do
Yeah.
anything in your time slot. That's what it's doing.
So,
So
okay,
yeah.
sorry, please continue.
Yeah, that's it. It will sleep again and again. It will change it to sleep, and then it will be running that.
So, one more question in this regard that I have is, so the wait function that the parent calls, if,
Yeah.
for example, so what I understood is that if there is one child of that parent that has exited and is in the zombie state, then the wait function that will get, I mean, that will get called.
Yeah.
I mean, sorry. Yeah. So, my question is, if there are multiple children and say multiple of them have exited, so is there any specific order in which the wait function gets called, or how does that work in case of multiple children?
So multiple children in the sense you have to fork 2 times, right?
Yeah, yeah. Say, let's say there are multiple forks in that parent process.
Okay, so multiple fork in the parent process will, yeah, okay. So this will
I mean,
only wait for one
I,
children. So one wait call will only wait for one children, and it can be any of the children. So that's why we are returning the process ID to check what children is exited, what children
okay.
exited. So we have to use, so if you are using 2 forks, you have to use 2 waits to wait for those 2 processes. And whenever
Okay.
one fork when one wait,
Hello.
I think he got disconnected.
Hello.
Yeah. Yeah.
My voice is very low. Maybe you can.
Yes, sir, we can hear you. Yeah.
okay,
Okay.
okay, I think there is some problem in the network.
Yeah. So the last thing I heard from you is whenever one child gets called or something,
Yeah,
one fork is called.
one child get exited, it will, the wait system call will return that child. So we identified which child exited using the PID.
PID. Okay. So I mean, this question came to my mind because one of the options in that question was what happens if there are what happens if there are multiple children. I think the first
Yeah,
option was talking about an infinite loop until all the child processes are terminated.
no,
So
that's why
I
I
mean
asked this question.
yeah. Okay.
Only one child you will, so you have to write the code in such a way, like you will write a code in such a way that the main code will be if condition and the PID of the current process, right? So you have to also
Yeah.
write the code. If you want to handle different signs in a different way, you have to write that accordingly. You have to use some if condition to check for if the returned process is this, do this, else that, things like that.
Okay. Okay. Got it. Got it. Thank you, sir. Thanks for that.
Yeah. Okay, so then we'll finish it.
Finish this.
Thank you.
Thank you, sir.
Thanks for the session.
Yeah, thanks.
Thank you. Good night.
Good night.